Everybody. In today's lecture, let us discuss about minimization of spherical aberration. So already we know that the failure or inability of the lens to form a point size image for a point size object, we call it as spherical aberration, right? Already in my last lecture I explained about this spherical aberration, why it will form, and what are longitudinal and lateral spherical aberration, what is circle of least confusion, right? Now check it. Now let us see how to minimize this spherical aberration. So in my last lecture I said that the spherical aberration is due to the focal length varies with the radius of circular zones. As focal length is changing with the radius of circular zones, marginal rays will have lesser focal length, paraxial rays will have greater focal length. Due to that only we are getting a spherical aberration, right? Then there are nearly 6 ways to minimize this spherical aberration. The first one is by means of stops. Okay, by means of stops. So here what we will do means, the stops we are using are of such a nature that it will stop marginal rays and permits paraxial rays, or stops paraxial rays and permits marginal rays. So any one ray will be stopped and other ray will be permitted in order to get a point size image for the point size object, right? Now next, the second method is by using plano-convex lens, or we can also say by dividing the deviation equally. Okay. Now here it has been observed that spherical aberration is directly proportional to the square of total deviation produced by the lens. Total deviation produced by the lens. So that is spherical aberration proportional to dou square. Let the dou be the deviation. So total deviation we are saying, so dou 1 plus dou 2 whole square, or we can also write it as dou 1 minus dou 2 whole square plus 4 dou 1 dou 2. Now when dou 1 is equal to dou 2, what happens? This will be 0 and spherical aberration is only due to 4 dou 1 dou 2. No? Means spherical aberration will be minimized. When the spherical aberration is minimized, when the deviation on either side of the lens is equal to each other, then only the spherical aberration will be minimized. Then how to place the plano-convex lens to reduce the spherical aberration? So first what we did means, we placed the convex surface of a plano-convex lens towards the rays, light rays. Then here the deviation is equally distributed at either sides, or we can say that on either sides we will have deviation, or deviation will occur on either sides, right? So now spherical aberration becomes minimum. Now if we place the plane surface of plano-convex lens towards the light rays, the deviation will be only at a convex surface. The total deviation will be only at a convex surface. We will not have any deviation at a plane surface. So here spherical aberration will be more. So now from this explanation what we understood, in order to reduce the spherical aberration, the convex surface of the lens must face the light. The convex surface of the lens must face the light. In such a way, we can minimize the spherical aberration. Right? Now next, by using two suitable lenses in contact. Now if we see the convex lens, now see, this IM is the image due to marginal rays and this is the image due to paraxial rays. Now here IM is towards the left side of IP for convex lens, and here IM is towards the right side of IP. If we see the IM, marginal rays image, it is left side to IP in convex lens and right side to IP in concave lens. So if we as it is in such a way, if we combine these two lenses in such a way, the convex, concave, then the lens may be free from spherical aberration. Now next, fourth one, by using crossed lenses. By using crossed lenses. Now here, mathematically it is proved that the deviation by two surfaces will be best and equal if R1 by R2 is equal to 2 mu square minus mu minus 4 by mu 2 mu plus 1. For such equation, the deviation by two surfaces will be best and equal. Now here R1 and R2 are radii of curvature. These two are radii of curvature of two surfaces, right? And here mu is nothing but the refractive index of lens material. Now the lens satisfying this condition, we call it as crossed lens. The lens satisfying this condition, we call it as crossed lens. Okay. Now if mu equal to 1.5, R1 by R2 value will be minus 1 by 6. If mu equal to 1.66, R1 by R2 value will be minus 1.1 divided by 6.5. And if mu is equal to 1.686, R1 by R2 will be equal to 0. So the crossed lens is nearly plano-convex in these two cases, but in third case it totally serves as plano-convex lens. Okay, in third case it totally serves as plano-convex lens. So we have to choose mu equal to 1.686 so that it serves as plano-convex lens, and we will use this to reduce the spherical aberration. Now next, the way of minimizing the spherical aberration is by separating the two plano-convex lenses at a distance. Then to reduce spherical aberration, how much distance must be kept means D must be equal to F1 minus F2, where F1 minus F2 are the focal lengths of two lenses. Okay, if we can place this much distance between two plano-convex lens, then this combination will be free from spherical aberration. Now the lastly, by using aplanatic surface. So what is aplanatic surface? Aplanatic surfaces means the optical surface in which every point on surface and where the sum of optical distance between any two fixed points in the space will be constant. Okay, at every point On the surface, the sum of optical distance between two fixed points will be constant. Such surfaces we call it as aplanatic surfaces. So now why these aplanatic surfaces are used means to produce point size image. For producing for producing point size image. So by using any one method, we can, out of these 6 methods, we can minimize spherical aberration. So thank you for watching my video. If you like my video, share, subscribe my channel Reshma Physics. Thank you.